The second elimination reaction is called an E1. E stands for elimination, 1 for unimolecular, only one molecule at the transition state. So if we run this reaction right here, it has a protic solvent, room temperature. You actually get, and if we mark the alpha carbon, and of course you have beta hydrogens all over, like here, there, and there. You would get the following product. So you'll get an elimination reaction. Of course, in addition to that, you will get if you recall, the substitution product. So this is SN1 and this is E1. We'll talk about this more in depth in the next few pages. You should be aware that, so that's your E1. By the way, E1 and E2 give you the same product. So there's no difference, just like SN1 gave you the same product as SN2, of course, with some stereochemistry changes, like inversion versus a racemic mixture. So the mechanism of an E1 I mean, is that it's 2 steps. The first step, which is the rate limiting step, I'm not sure why these keep disappearing, these dots. So that's your slowest step. Just like in SN1, the first step was the slowest step, is actually the breaking of the leaving group and the carbon bond, which would yield a positive right there. So that's the first step. And again, here's your alpha carbon and here's your beta hydrogen. Now the next step, which is a fast step, and I'm going to take this now, place it there. And again, I'm going to mark your alpha carbon. Is you have a base nearby. And notice the difference between E2 and E1. Base attacks the proton, and of course, the electrons would shift between the 2 carbons, the beta carbon, this is the beta hydrogen, to make a double bond. So that is the mechanism of E1. It's 2 steps, just like SN1 was 2 steps. The kinetics is that E1 is a first order, only depends on the alkyl halide. So you double the concentration of the alkyl halide, you double the rate, you double the concentration of base, which is the solvent, nothing happens. The energy diagram is also similar to that of the SN1 reaction. You have your reactants and you have your products. Once again, the difference between them is delta H. And of course, you have two steps, as you can see. Here are your two steps. So step one is breaking the carbon, in this case, bromine, as you saw in here. It's related to this reaction. Carbon-bromine bond. So let's draw the transition state. So you have, of course, methyls here. So that's a delta minus, and of course, this is delta plus because it's forming a carbocation, as you can see down here. And of course, there's a second transition state. I'm only interested in you drawing the first transition state, just the main one. Now, the leaving group. Remember, we always need good leaving group. I would be a great leaving group. It's better than Br, better than Cl. And if the more, the better. In fact, I actually switched this right here. The alkyl halide is also similar to SN1, which is tertiary, secondary, better than secondary, primary, and of course, methyl. In fact, there's no reaction at the primary or the methyl. So we need more substituted simply again to stabilize the carbocation. With the base, luckily these are becoming quickly to discuss, is that E1 does not require a strong base. So we need a weak base, and that's generally the solvent molecule. So once again, if we have ethanol, if we have water, if we have methanol, propanol, whatever it is, these are all solvent molecules. And again, these are weak bases. Solvent, as we just spoke about it, is we need a polar protic solvent to stabilize the carbocation intermediate, as I told you right here. And of course, the resulting product must follow Zaitsev's rule. Nothing has changed. So in this case, if we have an example, and again, if I'm only paying attention to the E1 reaction, then I would carefully investigate where would my alpha carbon be, and it's right there. And of course, if you notice, you have 3 beta carbon or 2 beta carbons, this one and that one. Now, in skeletal structures, you have to, let me erase it, move it out of the way here, just put it down here for space. You have to recall Zaitsev's rule. Remember, this one has 1H, we don't show, but here we need to show them for these kind of reactions. So Zaitsev's rule says, when you remove the proton, you remove it from the one that has the least or the most substituted beta carbon. And of course, it would be the one on the right. So your product then would be right there. That would be your product. If we would like to show the mechanism, it would be, remember, first step is breaking this bond. Right there. And of course, the next step would be the attack of the base at the proton. And if you notice, you're forming the double bond between the alpha carbon and the beta carbon. So that would be your resulting product. So once again, nothing has changed from in terms of the examining the factors. We will, in the next few pages, come ready, we will examine how now they compete with each other. And please pay attention very, very close to that part. And we will do more and more examples of these when we meet.